We are doing the OCR Chemistry AS Level 2019, and this is Section B. So this question is about atomic structure and the compounds of calcium, nitrogen, and oxygen. Most elements contain different isotopes. State two differences between isotopes of the same element. Okay, so straight up is a different number of neutrons, and so we will have a different atomic mass or a different mass number, and that results in different physical properties. So you could have had any two of the 3 points here. Complete the table for an atom and an ion of two different elements. Okay, so this is the first row. We have the protons, neutrons, and the charge. And we know, in order to fill this out, we know that protons is equivalent to the number of electrons. So if we have 26 protons, and we should have 26 electrons, especially since the charge is 0. So it tells us that we will have 26 electrons. Now, we know that to get the mass number, we have to do the protons plus the neutrons to get 54, which is the mass number. And in order to work out what element this is, we can go to the periodic table and look at the proton number. And we should see that 26 will give us Fe. So that's the first row. Now, the second row, we've got the mass number, we've got the electrons, we've got the charge. Okay, now it tells us this is an ion. So we have 36 electrons, but we have gained 2 electrons. That means that the original number of electrons is 34, and that is equivalent to the number of protons, so 34 protons. We know that protons plus neutrons gives us the mass number, so the mass number minus the number of protons will give us the number of neutrons, which we get as 46. And once again, now we have the proton number, we go to the periodic table and look for 34, and that gives us Se for selenium. Electrons occupy orbitals which are arranged in energy levels in the diagram below. Each box represents an orbital and each electron is shown as an arrow. Label the subshells and add arrows to show how electrons occupy orbitals on an atom of oxygen. Okay, so oxygen has 8 electrons, and we know that we start off with the 1s orbital, which occupies 2 electrons, so that's automatically 2 electrons we have here, giving us a remainder of 6. Then we move on to the 2s orbital, and that occupies 2 electrons as well. So now we have a total of 4 electrons, and we need 8. So after the 2s orbital, we have the 2p orbital, and electrons occupy orbitals singly before pairing up. So we have 4, and that gives us 5, 6, 7. Now it starts pairing up, so we have 8, and that gives us our 8 electrons. Calcium reacts with nitrogen to form calcium nitride, which is an ionic compound. Construct a dot and cross diagram for calcium nitride. Show outer electrons only and the charges on each ion. Okay, so this is an ionic compound because that's calcium is a metal and nitrogen is a non-metal, and we have a transfer of electrons. We don't have covalent bonding, and so the transfer electrons, calcium will lose its outer electrons, so it has 2 outer electrons, and it will lose that to nitrogen. So we're going to show calcium with a 2+ charge and no outer shell because it loses the 2 electrons in there, and we have a total of 3 calciums as shown here. Now the nitrogen, we know that nitrogen has 5 electrons in the outer shell, and in order to become stable it needs to gain 3 to form 8, and so that's the 3 electrons it has gained from calcium. And we have a total of 2 nitrogens, so we write 2, and therefore the charge will be -3 for each nitrogen atom, and in total the electrons are equivalent because we have 3 lots of 2+ charges, so that gives us 2, 4, 6, and we have 2 lots of 3- charges, and that also gives us 6. So we know that the electrons transferred are the correct number. So we've had a total of 6 electrons transferred here and a total of 6 electrons gained here. Calcium nitride reacts with water to form a solution containing 2 alkaline compounds, or 2 basic compounds. Write an equation for this reaction. Okay, so it tells us calcium nitride, which they've given us here as Ca3N2, and it reacts with water, so that's H2O, to form a solution with 2 alkalinic compounds, right? So we have to take a look at these and split them up. So calcium needs to react with water to form an alkalinic compound. So what could that be? Well, we know that when a metal reacts with water, it will give us a hydroxide. And here's calcium hydroxide, and calcium's in group 2. So it has a 2+ charge, and we know that hydroxide is a -1 charge, and so we need 2 lots of hydroxides to give us for 1 calcium, sorry. Now, let's see the nitrogen. The nitrogen will react with water to form another basic compound, which you would have learnt about. It's ammonia. So we will have the NH3, and so we've got our 2 products. Now we need to balance it out. We've got 3 calciums over here, so we need to add 3 over here, and we've got 2 nitrogens here, and so we need to add 2 over here. And as we can see, that will result in 3 oxygens here. We have a total of 3 oxygens here, and for the hydrogens we have 2, 4, 6 hydrogens here, and the other hydrogens here we will have 2, 4, 6, so we have a total of 12 hydrogens. Now we add 6 here, because now we have a total of 12 hydrogens, and here we have a total of, that's 2 oxygens, times it by 3, we get 6. So not 3, 6 oxygens on this side, and a total of 12 hydrogens on this side, and so we balance it out by putting a 6 in front of the H2O. Calcium reacts with oxygen to form a compound which has a giant ionic lattice structure. The diagram shows ions as circles in a part of a lattice. Complete the diagram by showing the symbols of the ions, including the charges. Okay, so I wrote calcium over here. You could have written oxygen over here, but because I chose to write calcium over here, it must connect to the opposite charge. So the 1 calcium here is connected to an oxygen and an oxygen. And the calcium over here is connected to an oxygen and oxygen. The oxygen here is connected to a calcium here, and a calcium here. So you could have started off by an oxygen here, but then these, instead of oxygens, you would have to add calciums. And so it's just connecting the positive charge with negative charges, and the negative charges are connected to the positive charge. Nitrogen forms an oxide with the formula N2O. A molecule of N2O is linear and has a nitrogen atom in the center. Draw a dot and cross diagram for an N2O molecule. Show outer electrons only. Okay, so yes, this was a bit difficult, but what helps us tells us that there's nitrogen in the center, so that's our N over here, and it's linear, so it's straight, and it's N2O, therefore the other N can go either on this side or on this side, and then oxygen goes on the other side. So what we needed to know over here is that nitrogen forms a triple bond with each other. So this is how N2 looks like, and so this is the triple bond over here. So, and therefore, this bond is known as a dative covalent bond because all the electrons are coming from the nitrogen atom. And so oxygen doesn't actually contribute its electrons to the bond, only the nitrogen is using its electrons to form the bond, and so it's called a dative covalent bond. A student carries out a titration to determine the concentration of some hydrochloric acid. The student titrates the hydrochloric acid against a standard solution of sodium carbonate. The equation is shown below. The student prepares 0.15 moles per decimeters cubed of sodium carbonate in a 250 centimeters cubed of volumetric flask. The hydrochloric acid is added to a 50 centimeters cubed burette. The student pipettes the sodium carbonate using a 25 centimeters cubed pipette. The student's burette readings are shown in the table below. The rough titer has been emitted. Complete the table by adding the titers to the table. Okay. So of course this is just minusing the final reading from the initial reading, and so when we do that, this is what we get. We get 24.2, 23.85, and 24.3. Calculate the mean titer of HCl to the nearest 0.05 centimeters cubed the student should use for analysing the results. And so what we use here is the concordant results, and it's 0.05 nearest to each other. But concordant results will do. And so as we can see this and this concordant, whereas this is not. And so that's why when we do the mean, we emit it, and so we add them together and divide it by the number of titers that we use, and we use 2, and so that gives us 24.25. And when they mean the nearest 0.05, it will be this number here. Calculate the concentration in moles per decimeter cubed of the hydrochloric acid. Give your answer to 3 significant figures. Right, so whenever there's titrations and we have a lot of information, this is what I like to do. I like to draw a box. and I start off by writing the equation. You only need to use the first half of the equation, which is given here, and we use that because of the ratio. So as we can see, 1:2 ratio. And so I start off by writing the ratio, and then I write concentration, volume, and moles. And then I plug it in with what they have given me and what I need to find out. And so we have sodium carbonate plus HCl, that's a ratio of 1:2. And I can see that with this question they want me to find the concentration of HCl, and so I get to HCl, I go to the concentration box and I write question mark. So I know that this is what I want. And I always know that C equals N over V. And so that's what I need to get in order to find my final answer. And so if I go up and I start picking out what I need. So I go through every number and see if it's useful to me. So student prepares 0.15 moles per centimeter cubed of sodium carbonate. So automatically I've gotten the concentration of sodium carbonate. So I go to concentration and I put 0.15. So I've used that up. In 250 centimeters volumetric flask, right? So people get confused here is they think that's the volume. Well, no. Tells you the student put this concentration in a volumetric flask that is 250 centimeters cubed. It doesn't tell you that the volume of sodium carbonate is 250 centimeters. It tells you that they put an amount of sodium carbonate in a volumetric flask that happens to be 250 centimeters cubed. And so this is not used anywhere in our calculation. The hydrochloric acid is added to a 50 centimeters cubed burette. Once again, it's telling you that they've added HCl to a burette that is 50 centimeters cubed. It doesn't tell you that they've added 50 centimeters cubed of HCl to a burette. It tells you they've added HCl to a burette that is 50 centimeters cubed. So that's not our reading. The student pipettes sodium carbonate using a 25 centimeters cubed pipette. Now, this is the volume of sodium carbonate because it tells you that the student pipettes sodium carbonate using a 25 centimeters cubed pipette. That means the volume of sodium carbonate they used is 25 centimeters cubed. So I go down to the volume and I add 25 centimeters cubed, but of course I need it in decimeters, so I convert it by dividing by 1,000, and it gives me 0.025. And so we've used this number. And then we scroll, and then we see that the other calculation we have is 24.25, and that tells us calculate the mean titer of HCl used. So now we know that 24.25 centimeters cubed is the volume of HCl used. So I go to HCl and I put the volume, but I divide it by 1,000 to convert it to decimeters cubed, giving me 0.02425 as the volume. Now, I've used everything I've been given, so I scroll down and I can see that I have concentration, I have volume for sodium carbonate. Therefore, I can work out the moles. And so to work out the moles, it's concentration times volume, which I've done over here. I've done the concentration times the volume. It gave me 3.75 times 10 to the power of minus 3. Now, the only thing you can move across these tables is the number of moles. That's the only thing you can move across, and we can see that we don't have a number of moles over here, but we know that's a 1:2 ratio. Therefore, I need to times this number by 2 to get the number of moles for HCl, and that's what I did over here, and that gives me 7.5 times 10 to the power minus 3 moles for HCl. Now, I've got the moles for HCl, and I have the volume of HCl. So I can use that to calculate concentration. So I do the moles divided by the volume, which is 0.02425, and that gives me 0.309 moles per centimeters cubed as the concentration for HCl, which is the answer of the question. In the titrations, the student measures volumes with a pipette and a burette. The pipette has an uncertainty of 0.04 centimeters cubed in the volume measured. The burette has an uncertainty of 0.05 in the volume measured. Determine whether the volume measured by the pipette or the volume measured by the burette has a greater percentage uncertainty. Right. So how do we calculate percentage uncertainty? We take the uncertainty, we divide it by the reading, and we times by 100. So if we go to the pipette, they've given the uncertainty, they've given it as 0.04, so that's our first step, divided by the reading. And when we go over here, the reading of the pipette, which we used over here, was 25. and so we divide by 25. Notice how we didn't convert, because here it's centimeters cubed, and this is 25 centimeters cubed, therefore we keep them as the same units. And then this percentage, we have to times by 100, which gives us 0.16%. Now, let's go to the burette. It tells us the burette is 0.05, so we've got the burette. And we have the reading, which, if we go over here, the burette was 24.25. It's not 0.5. Sorry, I meant it's not 50 centimeters cubed, because the burette has a total of 50 centimeters cubed, but we use 24.25 of the volume that is in the burette, so that's why the reading is 24.25. However, there's an additional step when it comes to burettes. We have to times the percentage uncertainty by 2, and that's because we do 2 readings on the burette. So the first reading is when we put the liquid in and we measure it up to 50, so that's our first reading. And then when we open the tap and then we wait for the colour change in the conical flask, we stop, we close the tap, and so we stop the HCl from running through, and we're going to take another reading by seeing where it stopped, and so that's our second reading. Therefore, we've taken 2 readings, and so we have to take the percentage uncertainty and times it by 2. Same thing, this also applies to scales as well, because in the scales you will sometimes measure by difference, so you will put the sample in like a beaker, and then you will tip out the sample and then measure the beaker again, and so that's 2 readings. And so scales and burettes, you have times by the percentage uncertainty by 2, and so we do 0.05 times by 2, and then we're going to divide by the reading, which is 24.25, and times by 100, that gives us 0.41%, and therefore the burette had the greatest percentage uncertainty. This question is about halogens and halides. The boiling points of the halogens are shown in the table. So this is what we have. Explain the trend in boiling points of the halogens. So straight away we can see that the halogen boiling points increases down the group. Now, explain. Because the number of electrons increases down the group, and so the number of London forces increases as well, and so that means there's more energy needed to break or overcome the intermolecular bonds, which are the London forces. Right, you are supplied with a sample of ammonium bromide. Describe simple tests that would identify the cation and anion present in ammonium bromide. Right. So, if we start off with the bromide ions, so testing for bromide ions, we know that we use silver nitrate, which is AgNO3, and that's because when you add silver nitrate to a sample that has bromide ions, the bromide ions will combine with the silver to form a cream precipitate, so that's our observation. And the equation for this is an ion equation, which is silver plus bromide ions gives us AgBr, which is the cream precipitate. So wherever it's in solid, because all precipitates are solid. Now, for the ammonium ions, we test ammonia by heating with sodium hydroxide, and that will give us observation of litmus paper turning blue. The equation for this is that if we use ammonium ions and we combine it with the hydroxide, we will form ammonia, and ammonia is what actually turns the litmus paper blue. So we form ammonia and water. The water won't affect the litmus paper, but the ammonia is basic, and so it will turn the litmus paper blue. Now, this question is about ammonia. In the industry, ammonia is made from nitrogen and hydrogen. This is a reversible reaction as shown in the equilibrium below. And explain how Le Chatelier's principle can be used to predict the conditions of temperature and pressure for the maximum equilibrium yield of ammonia. Right. So as we can see, if we start off with temperature, this is an exothermic reaction, and in exothermic reactions, when we decrease the temperature, position of equilibrium will shift to the product side, which is where ammonia is. And so that's why the answer is decreased temperature, because it's an exothermic reaction, so when we decrease the temperature, we get an increase in ammonia. Now, the pressure. When we increase the pressure, it will move to the side where there are fewer gaseous molecules. So we have 3 hydrogens, we have 1 nitrogen, so they give us a total of 4 gaseous molecules, and here we have a ratio of 2, so that's 2 gaseous molecules, and so this is the side. The side with ammonia is the side with the fewer gaseous molecules. Therefore, when we increase the pressure, position of equilibrium will shift to the side with the fewer gaseous molecules, and this is the product side with the NH3. And so we increase the pressure to cause equilibrium to shift to the product side. Right, using certain conditions, equilibrium has the equilibrium concentrations in the table. Oh, sorry, using certain conditions, equilibrium 24.1, which is this, has the equilibrium concentration in the table. Calculate the numerical value for Kc for equilibrium 24.1 under these conditions. Give your answer to an appropriate number of significant figures and in standard form. Right, so Kc is the products divided by the reactants, and of course it's in the brackets you have to put the ratio of the products. So if we start over here, the product was ammonia, and so if we go to ammonia, it is 0.862, which I've written over here, and has a ratio of 2. So I write an outside bracket of 2. Now the reactants, it's nitrogen, hydrogen. The nitrogen was a 1.25 with a ratio of 1, so I don't write anything outside the bracket. And hydrogen, we have 2.75 as written over here, but with a ratio of 3, so I write 3 outside the bracket. So if I plug this into a calculator, it will give me 0.0286. I convert it to standard form by jumping 2 spaces, so I get 2.86, and of course because we jumped 2 spaces, we're going to put minus 2. Ammonia is used to make nitric acid. The first stage of the reaction is shown below. So this is it. Calculate the enthalpy changes of formation. The standard enthalpy changes of formation are given in the table below. Given in the table. State the conditions of a temperature and pressure used for the standard enthalpy measurements. Right, so this is just something you have to learn. So temperature is 298 kelvins or 25 degrees Celsius, and the pressure is always 100 kilopascals. Calculate the standard enthalpy change of formation for nitric oxide. Give your answer to a whole number. Right. So when it's standard enthalpy formation, the arrows point up, and when it's a standard enthalpy combustion, the arrows point down. But that always depends on the number, what type of numbers they've given. So here they're giving us F, so standard enthalpy of formation, and therefore our arrows will point up in our triangle. In the bottom, if it's formation, then you write the elements, and if it was combustion, then you write the oxides. But you don't really get marked if you write it or not, so I just automatically draw a box. Okay, so what I do is I write the equation which they've given me, and I do the box from under, and because it's formation, my arrows are going to point up. I then plug it in with the values they've given me. So they've told me that the reaction is minus 908, so I've written minus 908 over here. And now for ammonia, it's minus 46, but I've got 4 lots of ammonia, so I times by 4, gives me a total of minus 186. Right, oxygen just an element on its own, so it's going to be 0. So even though it's a ratio of 5 times 0 is still 0. Now 4 NOs, but that's what we're trying to calculate. So I write 4 lots of X, which is the value I'm trying to work out. Now H2O, I have minus 242, and I've got 6 lots of them, so it's minus 242 times 6, which gives me minus 1452. Now I write it down in the equation. So my reaction goes from here to here. So as I can see, I'm going against these arrows because it's split like this, because that's the reactants products. So my arrows, I'm going against the arrows. So I need to convert these signs. So the minus 186 becomes plus 1886, and I write it down. The 0 is not going to affect the reaction. And then I proceed. I'm going with the arrows, so I keep the the signs the same over here. So minus 142 remains as minus 142, I put it in there. And we've got plus 4x, because that's what we're trying to find out. So we plug it in, and that gives us minus 908. So this is my equation. Now I need to solve for x, so I'm going to start moving things to the other side. So the easiest thing to start off is with a plus 186, so I take it to the other side, so I minus 186 from both sides, and that gives me minus 1092 over here. Now I've got minus 1452 over here, I take it to the other side by plussing it, and so I get plus 360. And so I'm left with 4x equals 360, so I divide by 4 for each side to get x on its own, and that gives me 90. So that's why my answer is 90. This question is about alcohols and alkanes. 3 alcohols, A, B, and C, are structural isomers of C4H10O. Each alcohol is refluxed with an acidified dichromate, and this is written over here. Draw the structures for the organic products. If there are no reaction, write none. Okay, so there are 3 types of alcohols. You can get primary, tertiary, secondary, and tertiary. And primary alcohols will oxidize to aldehydes, and from aldehydes will oxidize to carboxylic acids. Secondary alcohols will oxidize into ketones, and tertiary alcohols will not oxidize at all. And we can determine if it's primary, secondary, tertiary by looking at the alcohol group and see how many carbons are attached to the first carbon. So this is the alcohol group, and I go to the carbon that's attached to, so it's this carbon. Now, the number of carbons that's attached to this carbon will determine what type of alcohol it is. If this carbon is attached to one carbon, as seen over here, it's a primary primary alcohol. If it's 2 carbons, then it will be a secondary alcohol, and if it's 3 carbons in total, it's a tertiary alcohol, yes. And so because it's 1 carbon over here, this is a primary alcohol, and therefore we will oxidize to a carboxylic acid. Now, carboxylic acid will look like this because we have the OH group over here. We just add a double bonded oxygen to this carbon over here to get the carboxylic acid group. Now, this one, if we go to the alcohol and see it's attached to a carbon, how many carbons is that carbon attached to? That's 1, 2, 3. Therefore, it's a tertiary alcohol. Tertiary alcohols do not oxidize, and that's why we have none. Now, the third one, we have alcohol group here, attached to a carbon. How many carbons is this attached to? 1, 2. So it's a secondary alcohol, and they oxidize to ketones. And all that happens over here is that the hydrogen gets removed, and we form a double bond to the oxygen, as seen over here. Write the systematic name for alcohol C. Right, this is alcohol C. Just remove that. And remember, we have to take the longest chain, carbon chain. So if we go 1, 2, 3, that's only 3. But if we go 1, 2, 3, 4, that's 4 carbons. However, we always have to have the smaller number attached to the alcohol. Therefore, we have to count in opposite direction. So it's 1, 2, 3, 4. So I've got the longest chain of 4 carbons, and I've got the smallest number possible that could be attached to the alcohol. So 4 carbons is butane, and we have to say that we have to state where the alcohol group is attached to, so the second carbon, so it's butane 2-ol. Complete the equation for the complete combustion of alcohol A. So C4H10, O, and we know that complete combustion is just oxygen, and complete combustion will give us 2 products. It will give us carbon dioxide and water. Now we need to balance it. We have 4 carbons here, and therefore we have to add 4 in front of the CO2, and we've got 10 hydrogens, so we have to add 5 in front of the H2O. So now we have a total of 10 hydrogens. Now, how many oxygens? So if that's 8, it's 9, 10, 11, 12, 13. So we have a total of 13 oxygens here. And here we have so far 1 oxygen over here. And that oxygen we can play around with. So if we have 1 oxygen here, we need to add 12 more oxygens. And because we've got 2 over here, we can add 6. So that means 6 times 2, we have 12, plus the 1 oxygen, we get 13.